Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'm going to take an important topic in water chemistry, that is removal of hardness. Now, for removing hardness from water, there are different methods which are being used at a large scale. Those methods being the permuted process or zeolite process. Then the second method is ion exchange process. There is soda lime method. Then there is Calgon conditioning. And finally, we have reverse osmosis. So today I'm going to cover two topics. The first one being permuted or zeolite process. Permuted or zeolite process, and the second one being the ion exchange process. These are the two topics which I am going to cover today. So coming first to the zeolite process, what exactly we mean by zeolite? Zeolite or the permuted process or the boiling stones, they have a chemical structure of Na2O, Al2O3, XSiO2, Y water. So their complete structure is and this X and Y are variable. The value of X can vary from 2 to 10 and the value of Y, it can vary from 2 to 6. In general, these zeolites, they are hydrated sodium aluminosilicate minerals and they are capable of exchanging their sodium ions. They are capable of exchanging these sodium ions reversibly for the hardness producing ions which are present in water. There are certain natural zeolites which are found, but these natural zeolites, they are non-porous in structure. One example is natrolite, having the formula Na2Al3O3, 4SiO2 and 2 water. So zeolites, they are of two types. One is the natural zeolites found in nature, and the second ones are the synthetic zeolites which we have synthesized in the lab. So these synthesized zeolites, they possess gel-like structure and their exchange capability is much better than the natural zeolites. So these synthetic zeolites, they possess higher exchange capacity than the natural zeolites. Coming to the structure of zeolites, what happens? These zeolites, they are formed by the linking of SiO2 tetrahedra, where each oxygen is being shared by two silica. And at some places, these silica, they are replaced by aluminium. Oxidation state of silica is +4 and aluminium is +3. So to balance out the charges, at few places, sodium ions, they also get incorporated into the system. That means these sodium ions which are getting incorporated into the zeolites, they are not very tightly bound, they are loosely bound to the entire zeolite structure. So they can easily be replaced by the hardness causing ions which are present in water. So coming to the process, how the zeolite softener works. Here, there is a big chamber, there is an inlet for hard water. These are the sprinklers present. This is the zeolite bed. Then there is a layer of gravel. Then the soft water which is going to come out. This is a soft water outlet to sink. Finally, we have one injector also, and there is an NaCl solution or the brine solution. Rather than this is the brine solution, which is the saturated solution of NaCl. What happens is we pass hard water through the system. As you all know, the hard water contains calcium and magnesium ions. So when this hard water, it passes through the zeolite softener. When it passes through the zeolite softener, their exchange reactions take place. This zeolite softener, it contains labile sodium ions. So when the hardness causing ions, or when the hard water containing these ions or cations or the salts of hardness producing cations passes through the zeolite softener, exchange reaction takes place. These calcium and magnesium ions, they get incorporated into the zeolite bed. So when hard water is passing through the zeolite, calcium and magnesium ions, they get fixed into the zeolite bed, and equivalent amount of sodium ions move out into the water. So that means the hardness is removed from the water, but the water coming out from the zeolite, it is going to contain excess amount of sodium salts. Then this water passes through the gravel, and finally the soft water comes out through the soft water outlet. So after some liters of hard water has passed, this zeolite bed, it is going to get saturated with calcium and magnesium ions, and there all the sodium ions are going to get converted into calcium and magnesium ions. Then the exchange capacity of zeolite bed is going to get reduced. So to use the zeolite bed again, we have to regenerate it. And for the regeneration, what we do, we utilize this saturated solution of NaCl. We stop the flow of hard water, and now we start the flow of brine through the injector, and we now start spraying the brine solution. So brine contain excess amount of sodium ions. When this solution passes through the zeolite, again these calcium and magnesium ions, they are going to move further out with the solution, and the sodium ions are again, they are going to get incorporated into the zeolite bed. So for regeneration, NaCl solution, when it is passed through the zeolite bed, sodium ions are incorporated back into the solution or into the bed, and the outgoing water, it is going to contain excess amount of calcium and magnesium ions. And now this water containing excess calcium and magnesium, it is shown out through the sink. This is stopped, and now the water flows out through the sink. After washing with water, brine has already passed. So after washing the zeolite bed with water, clean water, it again becomes capable of passing the hard water to exchange the calcium and magnesium ions through it. Clear? So the regeneration, after some time, the zeolite, it is completely converted into calcium and magnesium zeolites, as I've already said, and it ceases to soften water. As a result, it is going to get exhausted. So at this stage, the hard water supply is stopped, and this exhausted zeolite, it is reclaimed back by treating it with a bed of concentrated NaCl. So this reaction takes place. Calcium or magnesium zeolites, on taking the NaCl, they are going to get converted back into sodium zeolite, and the outgoing water will have the different salts of calcium and magnesium. And the washing that are led to the drain and the regenerated zeolite bed, it is thus obtained, and it can be again used for softening process. Now, we can soft hard water, but there are certain limitations for using the zeolite bed. What exactly are the limitations? In zeolite process, 2 sodium ions are replaced by calcium and magnesium ion. That means the soft water, it is going to have excess amount of sodium ions. And if water that we are passing through the zeolite bed, it should not be acidic. If it is acidic, then the acid is going to destroy the zeolite bed. The linkages are going to get broken. If water is turbid, then the turbidity should be removed before feeding the zeolite, before feeding the water to the zeolite bed. Then, if this water which is getting passed through the zeolite, it contains excess amount of iron and manganese, then these iron and manganese ions, they fix permanently into the zeolite bed and they cannot be removed. That means the regeneration of zeolite beds that become very difficult. Then, if bicarbonate and carbonate ions, they are present in water, then they are converted into sodium salts, resulting in the alkalinity of water. Another one drawback is that anions are not removed. In the process or in the reactions, you can see that there is only exchange of cations. Anions are being passed as such into the outgoing water or the soft water. So, anions are not removed in the process. Now, there are certain advantages of the process. The first advantage is that hardness of water is removed, and the outgoing or the soft water, it is going to have around 10 ppm of hardness. It is easy to operate and it requires less space. Another important application or the advantages is no precipitate in the form of scale or sludge is formed, because in lime soda process, the precipitates are generated. As the hardness of water increases, the precipitation, the amount of precipitate, it also increases. But in this process, as you can see, the outgoing water has anions along with the soft water, and calcium and magnesium, they get fixed into the zeolite bed. As a result, no precipitate, either soft or hard, scale or sludge is formed. And the process is automatic and it can also be made continuous, that you can keep on adding water and you can get a flow of soft water. And the process is cheap, as in case for regeneration, you require only NaCl. Now, coming to the numerical part of zeolite. Here, the hardness of 1 lakh liter of water, it was completely removed by passing it through a zeolite softener. The softener then required 400 liters of NaCl containing 100 gram per liter NaCl for regeneration. So, calculate the hardness of water. That means we know if this is the zeolite bed, we know we have passed 1 lakh liters of hard water, and this zeolite bed, it got fixed with calcium and magnesium, and the outgoing water had sodium ions. So, on passing 1 lakh liters of water, this zeolite bed needed regeneration, and for regeneration we required 400 liters of NaCl having the strength of 100 gram per liter. So, now we have to calculate or back calculate the hardness of water, how hard the water was which was passed through the zeolite softener. Now, what we can do, we don't know the hardness, but we know how much NaCl we are utilizing to remove the hardness. That means the hard water which was producing the hardness, it is equivalent to the NaCl which is being utilized for removal of the hardness, and we are utilizing the strength of NaCl is 100 gram per liter, and 100 gram per liter of NaCl, we are utilizing how much? 400 liters of NaCl. That means total NaCl that we are utilizing is going to be, when 100 is multiplied, 100 gram per liter is being multiplied by 400 liters. This is the total amount of NaCl being utilized. So, it comes out to be we have to dissolve 40,000 grams of NaCl for removing the hardness from the zeolite. Now, we cannot directly know the hardness. In water chemistry, calcium carbonate equivalence is taken as the hardness. Why? Because the molecular weight of calcium carbonate is 100, which makes the calculations easy, and it is the most insoluble salt which can be precipitated in water chemistry. So, for converting this into calcium carbonate equivalents, what we need to do, we are going to multiply it with the equivalent weight of calcium carbonate and divide by the equivalent weight of NaCl. Calcium carbonate molecular weight is 100 divided by 2 gives its equivalent weight as 50. And NaCl, because its N factor is 1, so 23 plus 35.5 is going to give you 58.5. This is the molecular weight or the equivalent weight for NaCl. They are one and the same thing. So by this calculation, we are going to calculate so much grams of calcium carbonate equivalents. So, suppose this is X gram. I'm going to show you the calculations also. Suppose this is X grams of calcium carbonate equivalents. So, this is the amount of hardness which has been generated. And this amount of hardness has been generated by 1 lakh liters of hard water. So, when 1 lakh liters of hard water was passed, X gram of calcium carbonate equivalents hardness was produced. So, 1 liter of hard water is going to produce how much hardness? This is going to be our answer. Clear? So, I am going to show you in the next slide. Here, the total amount of NaCl required for the regeneration. Total amount being 100 gram per liter. How much we were dissolving and how many liters we are using such kind of NaCl solution. So, total is 40,000 grams of NaCl was required, and you can see 58.5 gram of NaCl, which is the equivalent weight of NaCl, is equal to 50 gram of calcium carbonate equivalents. Their equivalents, that means 40,000 into 10 to the power 3. I was doing in grams, you can do it in milligrams. Milligram of NaCl is equal to 40,000 into 10 to the power 3 multiplied by equivalent weight of calcium carbonate divided by equivalent weight of NaCl. So, this much milligrams of calcium carbonate equivalent hardness was produced, and this much hardness was produced by 1 lakh liters of water. So, 1 liter of water is going to produce how much hardness? So, this is the amount of hardness which was produced by 1 lakh liters of hard water. Here I am taking another numerical also. An exhausted zeolite softener, it was regenerated by passing 150 liters of NaCl solution having the strength of again 150 gram per liter of NaCl. If hardness of water is 600 ppm, ppm and milligram per liter is one and the same thing. So, here hardness is given and we have to calculate the total volume of water that can be softened by this zeolite softener. So, again the total amount of NaCl which was required for regeneration, it is going to be per liter how much NaCl was taken and how many liters of such NaCl solution we had to use for the regeneration. So, this is the total amount of NaCl which was dissolved in water. Again, equivalent weight of NaCl is equal to equivalent weight of calcium carbonate. So, on multiplying with 10 to the power 3, so much milligram of NaCl, it is equal to 22,500 into 10 to the power 3 multiplied by 50 divided by 58.5. So, calcium carbonate equivalence of NaCl is going to be so much of hardness is produced by n liters of water, and 1 liter of water produces so much of hardness. So, the volume of water that was passed through zeolite softener is going to be equal to hardness produced by n liters of water divided by hardness produced by 1 liter of water. So the volume of water is going to be 32051.2 liters of hard water. So this much water was produced, then this amount of hardness was produced in the zeolite softener, for which we required so much grams of NaCl. Now, coming to the next method of water softening, which is known as ion exchange process or the deionization process or the demineralization process. Now, this ion exchange resins, it is the most recent method for the softening of hard water. And by using this ion exchange process, nearly completely all the salts can be removed from hard water. And the water which is going to be produced after passing through this ion exchange method is as good as the distilled water. Now, water contains two types of ions. You can see, or anything contains two types, cations as well as anions. Therefore, the ion exchangers are also of two types, anionic ion exchangers and cationic ion exchangers. Whether anionic or cationic, they are derivatives or they are the copolymers of styrene divinyl benzene, these which are the long chain organic polymers having microporous structure. Why microporous structure? Because when the water passes through these small pores, when if hard water is going to get passed, then the cations and anions are going to get entangled. Calcium chloride, suppose, so calcium plus 2 and Cl minus are going to get entangled into this ion exchanges, and the outgoing water will not contain any cation or anion. Now, cation exchange resins, such resins, they are going to contain acidic functional groups like the carboxylic acid or the sulfonic acid functional groups, and which are going to be capable of exchanging their H plus ions with the other cations present in water. And in general, they are going to be represented as R minus H plus. Similarly, the anion exchange resins, they are the resins of amino or quaternary ammonium or quaternary phosphonium or tertiary sulfonium groups, which on treatment with NaOH solution, they become capable of exchanging their hydroxide ions with the other anions which are present in the hard water. And the general representation of anion exchangers is R plus OH minus. Coming to the process of ion exchange, what we do, here you can see two exchangers in the columns. One is the cation exchanger, another one is the anion exchangers. All right. So first what we do, we take impure water or the hard water, it is passed through the cation exchangers. Cation exchangers R minus H plus. So when hard water is passed, suppose this hard water contains calcium ions, cations. It is going to contain calcium cations. When this hard water passes through this cation exchanger, what is going to happen? Calcium ions are going to get fixed into this, and the water which is coming out, equivalent amount of H plus, they are going to get removed from the cation exchanger, and the water which is coming out, it is going to contain H plus as well as the anions. So anions, suppose the salt was calcium chloride. So the anions which are going to come out from this system is just going to be, so the outgoing water will contain 2H plus plus 2Cl minus. Calcium, it got fixed here. For one calcium, 2H plus are being removed from the cation exchangers, and the anions, they are also going to move as such out from the cation exchanger. So here you can see water plus acid, it is passing. 2H plus, 2Cl minus, they are going to combine to form HCl. That means a weak acid is going to pass through this system, and this water and acid is going to pass through the anion exchangers. And these anion exchangers, R plus OH minus representation, here the anions are going to get exchanged for every OH minus. So the 2Cl minus which were left here, which moved out from the cation exchangers, now these Cl minus are going to get fixed into the anion exchanger. And for every Cl minus that is getting fixed into the system, equivalent amount of OH minus is going to pass out from the anion exchanger. Along with these, the H plus will not interact here. So 2H plus is also going to move out from the system. So H plus and OH minus, they are going to ultimately combine to form pure water. Along with this pure water, they are going to get dissolved gases, CO2, which is going to pass. So when we pass this water along with the gases through degasifier, the gases are going to get eliminated, and water, after passing through the steam jacket, we are going to get demineralized water. Demineralized, why? Because this water contains only H plus and OH minus, which are ultimately going to form pure water. Since there are no ions present, therefore this water is deionized, and no minerals are also going to be present, therefore this water is known as demineralized water. So after passing n liters of hard water, these cation exchangers and anion exchangers, they are going to get saturated. So after their saturation, we have to do their regeneration. And how we are going to regenerate them? We are going to use acid for the regeneration of cation exchangers, so that H plus again gets incorporated into the cation exchangers, and now the calcium ions or the magnesium ions, they move through the cation exchanger and they are going to pass through the washings and out of the system. Similarly, this anion exchanger, it is going to get regenerated by the alkali, use of NaOH. When this NaOH is passed through the anion exchangers, all the anions, whether chloride ions, sulfate ions, they are going to move out through the washings, and OH minus is again going to get incorporated into the anion exchangers. So we can again run the process or reuse the regenerated cation and anion exchanger. Now we always run the process in this manner. First through the cation exchanger and then through the anion exchanger. We never reverse the process, that we do not pass the water first through anion exchanger and then through cation exchanger. Why? Because you can see here that dilute acid is being formed. But if we pass the water first through anion exchanger, it is going to contain excess amount of hydroxide ions. As a result, alkali is going to get generated, and this alkali has the capability of destroying the cation exchanger. If you are going to pass the water containing cations and this hydroxide, these hydroxides are going to destroy the acid bed or the cation exchanger bed. So therefore, we always pass this water through cation exchanger first and then through the anion exchanger. These are the structures for the cation exchangers and the anion exchangers. Here you can see in the microporous side, they are the sulfonic acid groups. These are the where exchange reactions are going to take place. So calcium is going to get incorporated here, and the 2H which are going to present, it is going to move along with the hard water. Similarly, here quaternary ammonium anion exchanger is present having OH minus. So Cl minus will get incorporated here and OH minus will move along with the hard water. This is the process which I have already explained. The hard water, it is first passed through cation exchange column, which removes all the cations like calcium or magnesium, and equivalent amount of H plus ions are released into the cation exchange column. And the reactions that are taking place, 2 are H plus calcium ions, they are going to get R2 calcium plus 2H plus. Similarly, the same reaction runs for the magnesium ions also. After the cation exchange column, the hard water, it is going to pass through the anion exchange column, where all the anions are going to get removed, like sulfate ions or the chloride ions, which are present in water. And equivalent amount of OH minus, they are released from this column into the water. So the exchange reactions here, you can see the anion exchangers exchanging different anions, chloride ions, sulfate ions, carbonate ions. So these chloride, sulfate and carbonate, they are getting incorporated into the anion exchanger, and equivalent amount of hydroxide, it is moving out into the water. So ultimately, H plus and OH ions, they combine to form water molecule. And the water coming out from this exchanger, it is deionized or demineralized water. Coming to the regeneration, I have already discussed the exhausted cation exchangers. They are treated with dilute acids to again get regenerated. Calcium moves out or the magnesium moves out, and H plus, they are again incorporated into the cation exchange column. Similarly, the exhausted anion exchange column, it is regenerated by passing through dilute NaOH. And when we pass through dilute NaOH, the sulfate ions are going to move out, and OH, they are going to get incorporated back into the column. So again, we can now use this cation exchanger or the anion exchanger for exchanging the hardness causing ions present in water. So the advantages, this process is utilized to soften highly acidic or alkaline water, and water of very low hardness, that is less than 2 ppm, is produced. This advantages being, we are going to use 2 huge columns, so the equipment is costly, and if the water is turbid, then the output of the process is going to get reduced, or otherwise we should first remove the turbidity and then pass through the water through these ion exchangers. Thank you.